Good afternoon, everyone. Folks, this is a recording notice. This lecture is being recorded. If you have any concerns, you need to contact me, please. We were working on chi-square test. One of the problem with that method, or you guys also ask question, how do you decide about the intervals? The alternate method, or the second method that we can use is this is the second method. The first was your chi-square test. This is the second method, which is called Kolmogorov-Smirnov, which is also denoted as KS test. Now, the advantage of using this test is that we don't need to have the intervals for data. Now, there are some steps that we need to follow in this method. Step 1. To arrange data in an ascending order. Step 2. Calculate the observed CDF, cumulative distribution function, using this thing we discussed last time. Depending upon the number of the data, we have different formulas. We use f of x of I, and because this is an observed CDF, we just write down the cap on this. That is equals to I over n. This is used if number of, which is denoted as n, is greater than or equals to 25. We also have f of x of I is equals to I over n plus 1, and f of x of I is equals to I minus 0.3 over n plus 0.4. These two we use when we have n, the number of data points, are less than 25. And this thing is what we call as the mean rank. We studied last time. Mean rank. And this is called as the median rank. If your question does not specify which one you need to use, you can use either. Folks, I need to go to next slide, please. Now, step 3. Calculate the theoretical CDF using the assumed distribution. For example, if assumed distribution, if assumed distribution is normal distribution, then the theoretical CDF is defined as f of x is equals to phi of, this is what you have already done, x minus mu over sigma. If your assumed distribution is log normal, then your f of x will be phi of 1 over w log of y over y naught. If your assumed distribution is exponential, then your f of x is equals to 1 minus e power minus lambda of x. Now the next step, step number 4, is determine the maximum difference between the two CDFs. By that I mean to say we will take the difference between observed CDF and theoretical CDF. Folks, I need to go to the next slide, please. Now we take our theoretical CDF and subtract our f cap from this. This should be I here. F of x of I. And we take their absolute value, and then we find out the maximum value. And that's what is equals to your T of n. This T of n mathematically T of n is a random variable and its distribution depends on the sample size, which is denoted by n. Now the relationship between CTF and significance level is P of D of n, which is less than equals to T of n of alpha, that is equals to 1 minus alpha. According to KS test, if D of n is less than equals to T of n of alpha, this is n here, the assumed distribution is acceptable. With a significance level of alpha. This thing, that's what we find out using the tables. T of n of alpha just like chi-square test, we had a table. The same is for this method. So I'm going to show you about that table. This is the table, folks, that we use for the KS test. How do you read this table first? These are the values of your n, and these values on the top of D, these are the values of your L. So this is as alpha 0.2, alpha at 0.15, and so on. For example, if I have something like d of 6 at the value of 0.05, so what we need to do, first you need to decide about your alpha value. So this is the one which we are concerned with, because my alpha value is 0.0. The next is I need to go for the n value, which is 6 here. So with the n value of 6, just come to the corresponding value here. So that's your value of the d6 and 5 of alpha, which is 0.521. If your n values are greater than 50, these are the different relationships that you can, depending upon what is the value of your alpha. So for example, if I have the same thing, I have the d at 0.05, but my value is, let's say, 60. So this is the relationship that I need to use. This is a table that I will provide you when I will upload the lecture. Folks, I will go on the next slide, please. Now what I'm going to do here, the same example as we did last, the young modulus data, and we solved that example using the chi-square test. The same example I'm going to do here. So the first column in this method, that should be your I value, which was from 2, 3. And if you have work on that example, this was going up to 41 data points. In the first step, we need to arrange the data in an ascending order. So the second column should be E of I. When we arrange the data in an ascending order, it will turns out to be 25900, 27400, and so on. The last term is 33400. Now then you need to find out your F, which is the cap here. The formula that we are using it, because the data is greater than 25, I'm using it I over n here. So 1 divided by 41, this will give you 0.0244. 2 divided by 41, it will give you 0.0488. Now the same procedure will keep going until your last point should be 41 divided by 41. That turns out to be 1 here. Now in the next column, we need to find out our f of e. And if you recall, in the previous statement, he was asking to find out for distribution and the log normal distribution. So let's do it for the normal first. And then we will look for the log normal. In order to find out the normal distribution, what we will do, the value of your f of e for normal distribution I'm doing it I is equal to 1, this value. So the same procedure as we did last time, this will be your probability of Young's modulus value, which is less than 900. And we find out our CDF at this value, which is 25,900. And that is equals to your phi and x minus mu. The x is 25,900, and subtract the mu value of the data, which was 29576, divided by your sigma, which was 1507. So once you solve it, you get the value of 0.0073. That's the number which will come at this point here, corresponding to 1. It is 0.0073. The same procedure applies for the second, third, and I'm just going to write down the result for the second number. As you can see in this method, I'm not using any interval, just like we used in the chi-square method. This is the number for second. And the similar procedure, you will find out the last term turns out to be 0.9945. Now, similarly, for f of e for log normal, for log normal distribution at I is equals to 1, the formula that you need to use is the same, phi of 1 over log of y over y naught. Once you solve it, you will get the answer of 0.0051. For I is equal to 2, you will get the answer of 0.07, and the last terms will be 0.9922. Now the last column will be of d of n. Again, that should be for normal distribution, and it for the log normal. And if you recall, for this d of n, we will just take the difference between this one and this one for the normal. This out to be 0.0171. The difference between this and this is 0.0261, and up to so on. The last term is 0.0055. Now similarly, the dn log normal, it will be the difference between this, your f cap of e, and this value. This one turns out to be 0.193, and similarly this and this difference will be 0.0233, and you keep finding up to the last point, which is 0.0078. Now once you have this table, then you need to look for the maximum value. If you allow me to go back in the previous slide, this is what we are discussing here, that the number, we need to choose the maximum number from this. Now out of this table, the maximum number that we get is it is somewhere in between, which is 0.1018, and this number for the log normal turns out to be 0.899. These two numbers are what we need to compare for the d of n of alpha. Go on the next slide, please. Now we need to find out the d of NR41, and the alpha value in the question was 0.05. So the formula that we'll use is 1.36 over, this is from the table. This is coming from the table. That turns out to be 0.21. Now we just saw that for normal distribution, the value was 0.1018, which is less than the value of 0.21. So we'd say that's acceptable. The normal distribution is acceptable for the given data. Now similarly, for log normal, distribution, the value from our table was the maximum value 0.0899. This is also less than 0.21. So I can say that log normal is also acceptable for the given data. So both are acceptable. Both distributions are acceptable. Is better as value is smaller. By better, I mean to say it is more appropriate to use the log for the given data. Now, if you recall, this is the same result as we received from the chi-square method with the same question. Everything I did for this topic is on page 114 to 117. This is the book I shared on the scan pages on the D12. This is available on your D12. So I will go on the next slide, please. The last topic that we to work on is the maximum likelihood estimation. This is also called as MLE. This is used to estimate the unknown distribution parameters. The best estimate of unknown distribution parameter let's say theta 1 is the value most likely the sample data. If x1, x2 up to x of n are independent, the likelihood function is as capital L of x of I, which is 1 to x of n of your theta, which is the unknown distribution parameter, that is equals to the functions of f of x1 theta times f of x of 2 of theta, and up to the last term will be f of x of n of theta. Now this is what L is called as the likelihood function. Likelihood function. The likelihood function, we take our x, given that the theta, which is unknown parameter, that is equals to, now these are being multiplied here, so I can multiply them. This is the symbol that we use for multiplication. From I is equals to 1 to of f of x into x of I of theta. If you're not familiar with this is the for multiplication. This is the symbol for the multiplication. This will be the provide us the value of the theta that makes our L. Folks, I need to go to next slide, please. taking natural log on both sides. We have the natural log, which is represented as ln of n, of likelihood function of x given that theta, that is equals to the natural log of your multiplication of factor f of x of I. This is x of I of theta, and your I value is ranging from 1 to n. If you recall the property of the natural log, these are being multiplied, so I can add them up. Because I need to show it for more than one value, I will use my summation sign. I is ranging from 1 to n of the natural log of f of x of I of theta. Now in the next step, we take the derivative of this term and equate that equal to 0. Take derivative with respect to theta. So on the left hand side, this will be, let me write it down here. This is the same term, of course. So that will be this term. We take the derivative with respect to theta and we equate it equals to 0. From this equation, we can find out the value of our unknown parameter. How we do? I will take an example of geometric distribution. Let's take an example of geometric distribution. If you recall the PMF of geometric distribution, it was of x that was equals to r into 1 minus r x minus. This was the PMF, probability mass function of the geometric distribution. And in this one, the r was the failure probability. Which is your parameter for the geometric distribution. And we want to find out that parameter. I need to go to next slide, please. So my x, of course, x1 and x2 up to the value of x of n. Now I take the likelihood function here of x1, x up to x of n, given that my unknown parameter, this distribution, which is R. That should be equals to, I will take my PMF and multiply it of n. So for the first term, it will be R into 1 minus R power x1 minus 1 multiplied by the second term, which should be R into 1 minus R power x2 minus 1. Now this is the same formula. If you allow me to go back, please. This is the same formula here that I am applying that. And you keep multiplying it until you get your last term, which will be the R of 1 minus R power x of n minus 1. This R inside this equation is being multiplied by n times. So I can take R power n and then again use the multiplication symbol to summarize. So this will be the multiplication of 1 minus R into x of I, and your I is ranging from 1 to n. And the left hand side, this will be my likelihood function of x given that my parameter, which is R here. The next step was we will take the natural log on both sides. So taking natural log on both sides. So that will be natural log of likelihood function of x given that R, that is equals to. Now when I take the natural log of this term is being each other. So that one should be the natural log of R of n. According to the log property, I can add them up because they are being multiplied. So that will be your 1 minus R into x of I minus 1. So the I is ranging from 1 to n. Using the log property again, this power can be multiplied now. Plus, as you can see, these are being multiplied, these terms. So using the log property, I come in the summation. It will be the summation from x I is equal to 1 to n, and the natural log of this term 1 minus R power x I minus 1. Or I can also further simplify this as n of natural log plus the summation of, now this term is a power here, I can use it as the product here, x of I using the log property, and the natural log of 1 minus R. I is ranging from 1 to n. Now in the next step, we need to take its derivative that equal to 0 and find out the value of R. So I will go on the next slide, please. Now I take the derivative of this term. On the left hand side, this will be the derivative of natural log of L with respect to the unknown parameter, which is R in our geometric distribution. That is 2 n into. So if you look on your papers, this the derivative of log of R, that should be equals to 1 over R. The summation of x of I minus 1. This term will remain the same because there is no R in this. However, if you allow me to go back, please, this term, I will take the natural log of this, which will be 1 over 1 minus R, and the derivative of inside will be minus 1. This will be 1 over 1 minus R times minus 1, and we need to it equals to 0. So this will be n over R. This is the minus 1 over R, 1 minus R, and summation of x of I minus 1. I is ranging to n, that is equals to 0. Now we just need to solve it and find the value of our R, which is unknown parameter. So this is n over R minus 1 over 1 minus R. This one I can choose here as summation of x of I. Now the I is ranging from 1 to n. However, for this term, this will become n because I have the n number of data here. That is equals to 0. This negative and negative becomes a positive here. I can write down n over 1 minus R. That is equals to, I can equate this as 1 over 1 minus R of summation of x of I, where your I is ranging from 1 to n. The left hand side will be R into 1 minus R. So this term will be n minus nr plus nr. That is equals to 1 over 1 r summation of x of I. I is ranging from 1 to n. These two terms will be cancelled out, and I will have n over r into 1 minus r on the left hand side. Folks, I need to go to next slide, please. So on the left hand side, I have n over r in r. That is equals to 1 over 1 minus r of summation of x of I. I is ranging 1 to n. This term is cancelled out. I have n over r is equals to summation of x of I. Because I'm interested to find out the r here, unknown parameter for geometric distribution. I use it r is equals to, that will be the summation of I is ranging from 1 to n. So this is your final answer here. More appropriately, it is written as, we can assign any x here, x bar, as because this is the approximate value, we write down cap on this is equals to 1 over x bar. So that what gives you the distribution parameter in the geometric distribution. Your answer is also good up to this point. It is also good if you use this relationship. So this is what is the distribution parameter in geometric distribution. Now let's take an example. Folks, I will go in the next, write down the example statement, please. For a set of data, what is the data here? 100, 110, 125, 295, and 350. Using maximum likelihood estimator, find parameters find the parameter of geometric distribution. Now what is the solution here? We just figure out that the geometric distribution parameter is equals to 1 over x bar, and the x bar is the summation of your x of I is ranging from 1 to n over. So we need to add up our x values, which is the data here, 100 plus 110 plus 125, 295 plus 350 divided by the n. So the n, we just need to count them, 1, 2, 3, 4, 5. So there are 5 data points here. This will be 196. So my approximate value of the parameter in the geometric distribution is 1 over 196. That turns out to be 0.00510. That is your answer for this. In your book on page, these pages are also provided on D12 in the previous lecture. page 118 to 120, is discussing about normal distribution. We need to perform and see how it that. The procedure and the rules remain the same, and try for exponential distribution as well. Or you can also try for any kind of the distribution. These are in the book of Halder that I shared with you. Folks, I will stop it here, and if you have any questions, I will then happy to take those. Folks, I will upload this lecture on D2L, and just go through this, go through the page number of the books which I mentioned. I already provided you the scan copies on the D2L, so you don't have to go through the library and spend your time there. And ask me any questions which you might have. In your last lecture on Thursday, I will discuss about some format on your final exam. Thank you very much, everyone, and see you on Thursday then. Thank you.